That little battery in your phone just survived a manufacturing process so precise and complex that a single speck of dust could have ruined it completely. Right now, your battery contains materials that have been heated to temperatures hotter than volcanic lava, compressed with forces that could crush a car, and assembled in rooms cleaner than hospital operating theaters. But here's what's truly incredible. The same technology powering your device is now being scaled up to create battery packs weighing over half a ton for electric vehicles. How do you go from making something the size of a credit card to building energy storage systems that can power a 2-ton vehicle for 400 miles? The answer lies in one of the most fascinating manufacturing processes ever created by humans. What you're about to discover is a journey where chemistry meets engineering, where robots work alongside precision machines worth more than most houses, and where the difference between success and catastrophic failure is measured in micrometers. This is the incredible story of how rocks and liquids become the energy storage devices that are reshaping our world. But before any manufacturing magic can happen, we need to understand where these incredible materials come from and the extraordinary journey they take just to reach the factory doors. Deep in the Atacama Desert of Chile, something remarkable is happening that most people never see. Massive pools stretching for miles contain what looks like turquoise paint, but this is actually lithium-rich brine being extracted from underground reserves. The process is both simple and complex. Salt water gets pumped to the surface and left to evaporate under the desert sun for months, concentrating the lithium to levels where it can be harvested. What makes this incredible is that Chile, Argentina, and Bolivia together control over 75% of the world's lithium reserves, yet they're located in some of the driest places on Earth. The irony is striking. Producing the materials for clean energy requires enormous amounts of water in regions where water is more precious than gold. Meanwhile, halfway around the world in the Democratic Republic of Congo, a completely different kind of extraction is happening. Cobalt, the material that prevents your battery from exploding, comes primarily from this single African nation that controls nearly 70% of global cobalt supply. The mining operations here range from massive industrial sites with equipment worth hundreds of millions of dollars to small-scale artisanal mines where workers extract high-grade ore by hand. The cobalt journey is particularly fascinating because this metal determines your battery's safety and longevity. Without cobalt, lithium-ion batteries would be prone to overheating and thermal runaway, essentially turning your phone into a potential fire hazard. Yet extracting this crucial safety component happens under conditions that would challenge even the most experienced miners. In Australia, massive open-pit nickel mines operate with trucks so large they dwarf buildings. These aren't ordinary mining vehicles. We're talking about machines that cost more than most people's houses and can carry 400 tons of material in a single load. The nickel they extract will ultimately determine how much energy your battery can store and how far an electric vehicle can travel on a single charge. The graphite story is equally remarkable. While natural graphite exists worldwide, nearly all the processing happens in China because they mastered the art of transforming raw graphite into battery-grade material decades ago. This processing involves heating graphite to temperatures exceeding 2,800 degrees Celsius, hotter than volcanic lava, to achieve the perfect crystalline structure needed for lithium storage. Once these raw materials are extracted and initially processed, they begin an incredible journey to manufacturing facilities around the world. Lithium carbonate travels from South American salt flats to processing plants. Cobalt sulfate moves from African refineries to battery factories. Nickel sulfate and processed graphite make their way from various continents to the precise locations where battery manufacturing magic happens. The logistics alone are staggering. coordinating materials from 6 different continents to arrive at manufacturing facilities with pharmaceutical-grade purity requirements. Each material must meet specifications so tight that contamination levels are measured in parts per million. Quality certificates accompany every shipment, documenting everything from particle size to moisture content. The transformation begins in facilities that look more like spacecraft assembly centers than traditional factories. Picture walking into a battery manufacturing plant for the first time. The first thing that hits you isn't what you see, it's what you don't hear. These massive facilities, spanning areas larger than football stadiums, operate in almost complete silence. The air itself is cleaner than what you breathe outside, filtered through systems that remove particles smaller than viruses. Workers move around in full protective suits, not just for their safety, but to protect the incredibly sensitive materials from contamination. The raw materials arrive looking nothing like what they'll become. Lithium comes as white powder that looks like flour. Cobalt arrives as dark crystalline chunks. Nickel appears as metallic pellets. Graphite looks like fine black dust. But these ordinary-looking materials are about to undergo a transformation that borders on magical. The first step in this incredible journey is creating what engineers call active materials. And this process is pure chemistry wizardry. In massive reaction vessels that could hold swimming pools, these raw materials meet for the first time under conditions that would terrify most people. Temperatures soar beyond 1,000 degrees Celsius, hot enough to melt copper. Pressures build that could crush steel. Chemical reactions release gases that require special containment systems. During this synthesis process, atoms literally rearrange themselves into new crystalline structures optimized for storing electrical energy. It's like watching nature's building blocks reorganize themselves according to human engineering plans. The lithium, nickel, manganese, and cobalt dance together at the molecular level, creating compounds that didn't exist naturally anywhere on Earth until humans figured out how to make them. But here's what's absolutely mind-blowing. The recipe has to be perfect down to individual atoms. Too much nickel, and the battery becomes unstable. Too little lithium, and energy storage suffers. Engineers spend years perfecting formulations where success is measured in parts per million. It's like baking a cake where being off by a single grain of salt ruins the entire batch. The quality control at this stage is almost obsessive. Every batch gets analyzed using machines that can identify individual elements and their exact quantities. X-ray diffraction reveals the internal crystal structure to ensure atoms arrange themselves correctly. Even the particle size gets measured. Materials must be uniform within nanometer tolerances. Once the active materials are perfected, they enter the next phase of their journey, becoming electrode slurries. This is where battery manufacturing becomes part chemistry lab, part high-tech kitchen. Massive mixing systems combine the active materials with binders, conductive additives, and solvents in proportions measured with pharmaceutical precision. But unlike cooking, this mixing happens under conditions that would make a laboratory jealous. The mixing chambers are sealed environments where humidity is controlled to fractions of a percent. Temperature stays constant within half a degree. The mixing itself involves forces and speeds that would turn ordinary materials into dust, yet somehow create perfectly uniform dispersions of microscopic particles. For cathode materials, the process involves solvents so toxic they require special handling procedures. N-methylpyrrolidone, the primary solvent, is so dangerous that exposure limits are measured in parts per million. Yet it's essential for creating slurries that coat perfectly and maintain their properties throughout the manufacturing process. The anode process is equally fascinating but entirely different. Those graphite particles that traveled from processing facilities in China get mixed with water-based binders in systems that look like giant stand mixers but operate with precision that would impress a Swiss watchmaker. The graphite itself has already been processed at those incredible 2,800-degree temperatures to achieve the perfect crystalline structure for lithium storage. Here's something that shows the incredible attention to detail. The mixing time is critical down to the minute. Mix too little, and particles don't disperse evenly. Mix too much, and you can actually damage the carefully engineered particle structures. Advanced monitoring systems track viscosity, particle distribution, and flow characteristics in real time. Once the slurries are perfect, they begin their transformation into actual electrodes through a process that's part printing press, part precision engineering marvel. The coating process uses machines that cost tens of millions of dollars and move with accuracy measured in micrometers. Picture a printing press designed by rocket scientists. That's essentially what these coating machines are. Metal foils thinner than human hair move through these systems at speeds that would make your head spin, yet the coating thickness variation across entire sheets is less than the thickness of a soap bubble. The copper foil for anodes and aluminum foil for cathodes must be absolutely flawless. Any microscopic defect could create a weak point leading to battery failure. These foils are so thin that handling them requires special techniques. Too much tension and they tear, too little and they wrinkle. The coating heads themselves are engineering marvels. They distribute slurry across moving foil with such precision that the thickness variation is measured in single-digit micrometers across sheets several feet wide. To appreciate this precision, imagine painting a wall while blindfolded and having the paint thickness vary by less than the width of a bacteria across the entire surface. Advanced sensors continuously monitor the coating process. Laser measurement systems check thickness thousands of times per second. Weight sensors detect if coating density varies even slightly. Optical systems scan for defects invisible to human eyes. Any deviation triggers immediate corrections or stops the entire line. But coating is just the beginning. Next comes the drying process, where things get really energy intensive. The drying ovens stretch for hundreds of feet and consume electricity like small cities. These aren't ordinary ovens. They're precisely controlled environments where temperature, airflow, and humidity are managed with scientific precision. The coated electrodes pass through multiple heating zones, each optimized for different stages of solvent removal. Here's what makes this process incredibly complex. Removing solvent too quickly causes the coating to crack or peel. Remove it too slowly, and productivity suffers while energy costs skyrocket. The temperature profiles are engineered down to individual degrees at specific positions along the oven length. Solvent recovery systems capture and purify the evaporated solvents for reuse. These systems are so sophisticated they can separate and purify multiple different solvents simultaneously while meeting environmental regulations that limit emissions to parts per billion. The energy consumption is staggering. Some battery factories use more electricity for drying than entire neighborhoods consume. Advanced heat recovery systems capture waste heat and reuse it, but drying still represents one of the most energy-intensive steps in battery manufacturing. After drying comes calendaring, a process that transforms the appearance and performance of electrodes through applied pressure. Calendaring machines look like giant rolling pins, but they operate under pressures that could flatten cars. The dried electrodes pass between steel rollers under forces measured in tons per linear inch. This compression increases energy density by removing excess void space while improving electrical contact between particles. But here's the fascinating challenge. Compress too much, and you block the pathways lithium ions need to travel. Compress too little, and you waste space that could store energy. Finding the perfect balance requires understanding material properties at the molecular level. The pressure control is incredibly sophisticated. Advanced hydraulic systems adjust roller pressure thousands of times per second based on real-time measurements of electrode thickness and density. Even tiny variations in material properties get compensated automatically. Temperature control during calendaring is equally critical. Heat generated by compression could damage the electrode materials, so cooling systems maintain precise temperatures throughout the process. Some calendaring operations even use heated rollers to improve material flow while preventing thermal damage. Quality control during calendaring involves measuring properties that sound like science fiction. Porosity measurements reveal the internal structure invisible to human eyes. Adhesion testing ensures the coating bonds properly to the metal foil. Electrical resistance mapping identifies any areas with poor conductivity. After calendaring comes precision cutting that would impress a surgeon. The cutting process uses blades sharper than surgical instruments and harder than most metals. Diamond-coated cutting wheels slice through electrode materials with tolerances measured in fractions of millimeters. Any burr or rough edge could later pierce the separator and cause dangerous short circuits. The cutting patterns are optimized by computer algorithms that minimize waste while maximizing yield. Advanced vision systems inspect every cut edge to ensure quality. Robotic handling systems move the precisely cut electrodes without any human contact that could introduce contamination. Even the cutting debris gets carefully collected and recycled. In battery manufacturing, waste isn't just expensive, it's often hazardous and requires special handling procedures. Now comes the assembly phase, where individual components unite to create functional battery cells. The separator installation is like performing surgery with materials thinner than human hair. These plastic films contain millions of microscopic pores that must remain unblocked throughout the assembly process. Any tear or contamination could render the entire cell useless or dangerous. Winding machines create what looks like the world's most important jelly roll. Positive electrode, separator, negative electrode, separator. Layer after layer wound with tension controlled to fractions of a pound. Too loose, and the cell won't perform efficiently. Too tight, and the separator could tear. The winding process happens in controlled atmospheres drier than most deserts. Even trace moisture could affect cell performance, so humidity is controlled to levels lower than what instruments can easily measure. The winding chambers are pressurized with dry nitrogen to exclude any water vapor. During winding, electrical tabs get welded using laser pulses lasting milliseconds. These welds happen at temperatures exceeding the surface of the sun, yet the heat-affected zone measures less than the width of human hair. Advanced beam control systems create welds stronger than the surrounding materials while avoiding any thermal damage. Quality control during assembly includes tests that sound like science fiction. Electrical impedance measurements reveal internal resistance patterns. Acoustic monitoring detects sounds indicating assembly problems. Optical inspection systems identify defects invisible to human vision. Once assembled, cells enter their housing through processes requiring cleanroom precision. The cell cases are precision-engineered containers designed to withstand internal pressures while remaining lightweight. Sealing happens in atmospheres so dry, they make Earth's driest deserts seem humid. Even molecular-level moisture could compromise cell performance over its decades-long lifespan. Electrolyte filling represents one of the most critical steps in the entire process. The electrolyte is the battery's lifeblood. It enables lithium-ion movement between electrodes, but it's also toxic, flammable, and incredibly sensitive to contamination. The filling process happens under vacuum to ensure complete penetration into every microscopic pore. Advanced dispensing systems measure electrolyte quantities to within individual drops while filling thousands of cells daily. Any air bubble could create dead zones where energy storage fails completely. Electrolyte formulations are closely guarded secrets involving dozens of different chemicals in precisely controlled ratios. Additives measured in parts per million can dramatically affect battery performance and safety. Getting the chemistry perfect requires understanding molecular interactions that even advanced computer models struggle to predict. After filling comes formation, the moment when batteries come alive for the first time. Formation involves the first charging cycles under carefully controlled conditions. During this process, a protective layer called the solid electrolyte interface forms on electrode surfaces. This layer is absolutely crucial. It allows lithium ions to pass while blocking electrons that would cause short circuits. The formation process can take over 20 hours per cell and follows charging profiles engineered with scientific precision. Specific voltages and currents applied at exact times and temperatures determine the quality of that protective layer, affecting battery performance for its entire lifetime. Temperature control during formation is critical within fractions of degrees. Advanced climate systems maintain precise conditions while thousands of cells undergo this process simultaneously. Even small temperature variations can affect the protective layer quality, impacting performance for years. Formation consumes enormous amounts of energy. Some facilities spend more on formation electricity than small cities use total. Energy recovery systems capture electricity during discharge cycles and feed it back into the grid, but formation remains one of the most energy-intensive manufacturing steps. After formation comes aging and testing that determines each cell's destiny. Aging isn't simply letting batteries sit around. Cells are stored at precisely controlled temperatures and charge levels while internal chemistry stabilizes. Advanced monitoring systems track voltage, temperature, and other parameters continuously during this period. Quality control testing subjects cells to conditions more extreme than they'll face in actual use. Temperature cycling from Arctic cold to desert heat. Vibration testing simulating years of vehicle operation. Safety testing that deliberately tries to make cells fail in controlled ways. The grading process sorts cells into quality tiers with tolerances tighter than most precision instruments. Capacity measurements accurate to fractions of a percent. Internal resistance testing revealing microscopic variations. Self-discharge monitoring, identifying cells with even tiny defects. Only about 90% of cells meet the highest quality standards required for demanding applications. The remaining cells find uses in less critical applications, but nothing gets wasted in modern battery manufacturing. But individual cells are just components. Creating battery packs requires engineering integration that rivals spacecraft assembly. Module assembly connects dozens of cells using welding techniques originally developed for aerospace applications. Each connection point gets tested for resistance because even slightly poor connections create heat that leads to premature failure. Battery management systems represent some of the most sophisticated electronics ever mass-produced. These systems monitor every cell continuously and make real-time decisions affecting performance and safety. Modern battery management systems contain more computing power than early spacecraft while operating reliably for decades. Thermal management integration ensures temperature uniformity across hundreds of cells. Even small temperature differences cause some cells to age faster than others, eventually limiting entire pack performance. Advanced cooling systems maintain temperature variations within single degrees across massive battery packs. Safety system integration includes multiple independent layers of protection. Current interrupt devices that can stop thousands of amps in milliseconds. Pressure relief systems designed to safely vent gases during emergencies. Structural reinforcements protecting batteries during vehicle crashes. Final testing subjects completed battery packs to validation procedures that would destroy most electronic devices. Electromagnetic compatibility testing ensuring batteries don't interfere with other vehicle systems. Vibration testing simulating decades of driving conditions. Safety testing that deliberately creates failure modes to verify safe responses. The precision and complexity involved in battery manufacturing approaches the limits of current technology. Every step requires understanding physics, chemistry, and engineering at levels that push scientific boundaries. Yet the end result appears simple: clean, quiet energy storage that's revolutionizing how we power our world. From those remote mining operations to the finished battery pack represents one of humanity's greatest manufacturing achievements. Materials extracted from deserts, mountains, and underground deposits get transformed through thousands of precisely controlled steps, each critical to the final result. The journey from Chilean salt flats and Congolese mines to high-tech manufacturing facilities showcases the incredible global coordination required to create modern batteries. Every battery embodies decades of scientific research, billions of dollars in manufacturing infrastructure, and precision approaching the theoretical limits of what's possible. Yet we've only scratched the surface. Next-generation battery technologies promise even more incredible advances that will continue pushing the boundaries of energy storage. The next time you use any battery-powered device, remember the incredible journey those materials have taken. From extraction in some of the world's most remote locations to sophisticated energy storage through manufacturing processes that represent some of humanity's greatest technological achievements. If this incredible manufacturing journey amazed you, hit that like button and subscribe, because the technology transforming our world has so many more fascinating stories, and you definitely won't want to miss what's coming next.